All right, welcome back, Team BC. Please find the mini engage in packet 702 on page 3. Take just 6 minutes. Try questions 1 through 5 on your own. Really try to explore, make the key connection number 5. Pause the video, and when you come back, I'll be reviewing this. All right, here we go. Let's check in on 1 and 2 first. Sketch the area represented by this integral. This integral tells me the area starts at pi, starts at 0, and ends at pi, so I'm shading this area. Second one starts at 0, ends at pi over 2, shading this area. A couple other details that are important to notice. This is 1, whereas this is 2, and this is 1. So the graphs are not to scale with each other, but the axes are different. It's going to be important as we move down the page. We're going to solve this integral 3 and then solve this integral 4 using our evaluation theorem. So here we go. Antiderivative of sine is negative cosine of x. Evaluated from 0 to pi. I get negative 1 minus negative 1. This is 1 plus 1, which equals 2. So that tells me that the area right here is equal to 2. Let's look at the second integral now. Evaluating integral, so I'm going to take the antiderivative. I see I have 2 sine of 2x. 2 sine of 2x. So I have a composite function. Makes me think of my anti-chain rule from the previous lesson. So let's check that. I get, hold the 2 in front, then I get negative cosine, keep the inside, divide by that derivative of the inside function, and then I evaluate from 0 to pi over 2. When I simplify these 2's, I actually get negative cosine of 2x from 0 to pi over 2. I can then substitute those limits, and I get negative 1 minus negative 1. This equals 2 as well. Interesting. Both those are 2. So when I get to 5, your answer in 3 and 4 should be the same. You should have an answer for 2. Of 2 for both of these. If you don't, pause the video, rewind it, make those quick edits, and then let's go into number 5. So answers in 3 and 4 should be the same. Explain why this makes sense using the graphs and the integrals. So the integrals both came out to 2, so I know they're both areas of 2. So that second integral, area was 2, so this is also 2. Well, how is that possible? Let's think about it. This was sine of x, so that area is 2. This was 2 times sine of 2x. If I think back to algebra 1, I'm multiplying the input by 2. That's going to cause a horizontal compression. So I'm compressing the graph horizontally by 2. But then the 2 leading the front, that's going to stretch the graph by a factor of 2 as well. So if I compress by a factor of 2 and then stretch by a factor of 2, those are essentially going to cancel each other out. And these two areas are equal. So altogether, this makes sense because the graph on the right is a horizontal compression by 2 and vertical stretch by 2. These cancel out to make the same area. So if I perform 2 of the same transformations on a graph, 2 opposite transformations, like a compression and a stretch with equal opposite magnitudes, then we see they'll be the same area. So this is going to lead us into our notes in a moment, but there's a key thing we need to remember here. Taking this antiderivative was more complex than taking this antiderivative, but they are the same area. So if I can take a complex integral and make it into a simple integral with the same area, we could solve the second integral, and then because we know they're the same area, it's going to be the same as that complex integral. So I pause the video here and make sure that you have those key ideas down. We'll be starting some notes in the next part, so make sure you have your notebook so you can capture these.